Tonight, we're going to talk about the first crew to actually live on Mars, and what's waiting for them once training ends and the real mission begins. Every astronaut selected for this journey will spend years preparing, running through simulations, isolation studies, and physical drills designed to ready them for nearly every scenario engineers can predict. But there's a category of challenge that sits outside anything a simulation on Earth can produce, because it only exists the moment a human being is actually standing on that surface, permanently, with no way back. By the end of tonight, you're going to understand exactly what that first crew will be up against, and why so much of it has nothing to do with the dangers most people picture when they imagine a mission to Mars. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Picture the moment of landing. You have just spent 7 months inside a spacecraft roughly the size of a large camper van. 7 months of floating in microgravity. 7 months of recycled air and packaged food, and the low, mechanical hum of life support systems that never stop. 7 months of watching Earth shrink from a planet to a bright star to something you have to search for, deliberately, in the dark. 7 months during which Mars grew from a small orange dot into the enormous, rust-colored world now filling your window. And now, the engines have cut. The landing legs have settled. The dust cloud, kicked up by the descent engines, is clearing. The instruments confirm what you already know intellectually, but cannot quite fully believe. You are on Mars. The first crewed mission to another planet in human history has just succeeded in its most basic objective. You are alive. You are here. And immediately, without pause, without ceremony, the checklist begins. Because Mars does not give you a moment to absorb it. It never will. Your body, before we even get to what the planet does to it, is already compromised in ways that matter enormously for what comes next. 7 months of microgravity left marks that will not disappear quickly. Bone is living tissue that constantly rebuilds itself in response to mechanical stress, to the load of carrying your own weight. Take that load away, and the body quietly decides it can function with less. Bone mineral density drops at roughly 1 to 2% per month in microgravity. Over 7 months, that is a 7 to 14% reduction, concentrated in the weight-bearing bones. The femur, the tibia, the vertebrae, the pelvis. The result is a skeleton measurably more fragile than when the crew launched. Fracture risk is elevated. Cortical bone walls are thinned. The internal scaffolding of trabecular bone in the ends of long bones partially dismantled. Muscles have atrophied in parallel. The crew will have exercised 2 to 2.5 hours every single day during transit. Intensive resistance training, cardiovascular work, equipment specifically engineered for microgravity. It is exactly what is prescribed for International Space Station crews. And it is still not enough to stop the loss. Studies of ISS crew members on 6-month missions following the same protocols consistently document muscle mass losses of 15 to 20%, concentrated in the lower body and core. 7 months is longer. The cardiovascular system reorganized itself for a world without gravity too. On Earth, the heart works continuously against gravity to push blood upward to the brain. In microgravity, that work disappears. The heart adapts, becomes slightly more spherical, its walls thin modestly, and blood pressure across the system drops. The whole circulatory architecture adjusted over 7 months to a world without weight. And now, Gravity is back. Mars gravity, 38% of Earth's. Not enough to feel normal, but enough to feel heavy after 7 months of weightlessness. The circulatory system must immediately begin meeting a demand it has not met for 7 months. Orthostatic intolerance, the dizziness and lightheadedness of a cardiovascular system not yet ready to push blood efficiently upward, will affect every crew member in the first hours and days on the surface. This is the starting point. 7 months depleted, every system readjusting to gravity. And Mars does not wait for any of it. The first time a crew member steps outside, even before the formal EVA protocol begins, is a moment of profound sensory disorientation. Not emotional disorientation. Sensory. Mars has an atmosphere, but it is so thin, roughly 0.6% of Earth's surface pressure, that it barely transmits sound. Sound is a mechanical pressure wave. It requires a medium to propagate through. On Mars, that medium exists, but is so sparse that sounds that would carry effortlessly through Earth's air are attenuated almost completely before traveling any useful distance. The result is that the Martian surface is not silent the way a soundproofed room is silent. It is silent in a qualitatively different way. There is no ambient acoustic texture, no hum, no natural environmental sound. You can see the dust moving in the wind. You can feel vibrations through your boots if you press your feet firmly against the ground. But the acoustic channel through which humans orient themselves to their environment, the constant background flow of environmental information that arrives as sound, is essentially removed. Humans depend on ambient sound in ways we largely do not notice because it is always there. It tells us where we are. It tells us the scale of the space around us. It gives us feedback on our movement. It regulates our nervous system through patterns of stimulation that evolved over millions of years of life in acoustically rich, natural environments. The rustle of wind through vegetation, the movement of water, the sounds of other creatures, birdsong, rain on a surface, distant weather, human voices. These sounds anchor us in an inhabited world. On Mars, none of them exist. Studies of genuine acoustic isolation, even for short periods, show measurable psychological effects. Anxiety increases. Concentration degrades. The brain, which evolved to continuously process environmental sound as a background regulatory signal, becomes dysregulated when that signal disappears. People in complete acoustic isolation begin experiencing phantom sounds, the brain generating internal auditory content to fill a void that evolution never designed it to sustain. Within hours, the Mars crew will have operational noise inside their suits. The sound of their own breathing, amplified by the closed environment. The hiss of the air, supply cycling. The hum of suit electronics. The voice communications channel. But the external world they move through will be acoustically almost non-existent, and they will be in that external world for hours at a time, on EVAs, for the full duration of the mission. This is not something that acoustic isolation training in a laboratory prepares you for at the scale of years. Because the duration is different, and because on Mars, the acoustic silence is never experienced in isolation from everything else. It is one layer of a complete environmental alienness that is always present simultaneously. The color of the sky matters more than most people would expect, not aesthetically. Biologically, the sky on Mars is not blue. During the day at the equator, it is a pale pinkish tan, sometimes shifting toward butterscotch brown near the horizon, moving through dusty orange and muted violet as sunset approaches. The light itself has a different quality in multiple dimensions. It is dimmer. Mars receives only about 43% of the solar energy that Earth does, because it sits roughly 1.5 times farther from the Sun. Not dramatically dimmer in the way that a cloudy day on Earth feels dim, but noticeably less bright than a clear Earth noon. It is also spectrally shifted in a direction that matters for human biology. Martian atmospheric dust scatters red and orange wavelengths more efficiently than blue ones. On Earth, the opposite happens. Atmospheric nitrogen and oxygen molecules scatter blue light preferentially, which is why Earth's sky is blue. On Mars, dust scatters the red end of the spectrum, giving the sky its characteristic color and shifting the overall light environment toward longer wavelengths. The human circadian system is synchronized primarily by light, specifically by the blue spectrum content of ambient light. Specialized retinal cells, distinct from the cells that handle vision, detect the presence and absence of blue spectrum light and use this signal to set the biological clock, regulate cortisol and melatonin release, and time the cellular processes that govern sleep, waking, metabolism, and immune function. On Mars, the blue spectrum content of the outdoor environment is reduced compared to Earth. The total light level is reduced. The temporal pattern of light through the sol is similar in structure to Earth's daily pattern, but different in its specific characteristics. The habitat will have interior lighting designed to compensate. LED arrays, calibrated to provide the biologically appropriate light spectrum at the right intensity and at the right times of sol. These systems are well engineered. They are an active area of research in space, medicine, and in the architecture of confined environments. They help substantially. They are competing with an external visual environment that delivers the wrong signals every time a crew member looks out a window, every time they come inside from an EVA, every waking hour of every sol for the duration of the mission. The Martian sol is 24 hours and 39 minutes long. The 39-minute difference from Earth's 24-hour day sounds negligible. It has measurable physiological consequences that accumulate over time. The human circadian rhythm is not a rough daily schedule. It is a molecular-level timekeeping system embedded in virtually every cell of the body, from neurons to immune cells to liver hepatocytes. The biological clock in each cell runs on an approximately 24-hour cycle, kept synchronized by light signals from the eyes and by social and behavioral cues. This clock governs the timing of hormone secretion, including cortisol in the morning and melatonin at night. It times the release of growth hormone during sleep. It regulates the activity of immune cells, the expression of DNA repair enzymes, the production of digestive enzymes, the sensitivity of insulin receptors, and dozens of other physiological parameters that are not constant through the day, but cyclic, rising and falling in coordinated patterns that the body depends on running in the right relationship to each other. Disrupt the timing of these cycles relative to the external environment, and you disrupt the coordination. The medical literature on circadian disruption is extensive and consistent. Shift workers, whose sleep-wake schedule is chronically misaligned with the environmental light cycle, show elevated rates of metabolic syndrome, type 2 diabetes, cardiovascular disease, depression, anxiety, immune dysfunction, and certain cancers compared to people with aligned rhythms. These associations are large. They represent the documented health cost of chronic circadian disruption in a real population over working lifetimes. On Mars, the crew faces a rolling 39-minute drift every sol. The drift is not constant in its relationship to biology. At some points in the cycle, the crew's sole schedule is closely aligned with their biological rhythms. At other points, it is significantly misaligned. The pattern cycles continuously, never settling. Habitat lighting systems, calibrated to Mars Sol time, will help by providing the biological light signals at the right times within the Sol. Individual response to circadian adaptability varies substantially. Some people adapt readily to shifted schedules and show minimal functional impairment. Others suffer significantly from even small shifts. The crew will have been assessed for circadian adaptability as part of selection. The data on how people perform on years of Mars Sol schedule, with this specific 39-minute drift, does not exist, because no human being has ever lived it. The first crew will collect that data by living it. The dust on Mars is a physical reality that affects the mission on multiple levels simultaneously. Martian dust is extraordinarily fine. Particle sizes commonly range from about 1 to 3 microns, with a significant fraction finer still. To visualize that scale, a human hair is roughly 60 to 70 microns in diameter. Martian dust particles are commonly 20 or more times smaller than a human hair, and the finest fraction is smaller yet. Particles this fine have two properties that make them operationally significant. First, they remain suspended in the Martian atmosphere for weeks to months following a disturbance, such as a wind event or a dust devil. They drift on the extremely tenuous atmospheric currents and settle very slowly. The atmosphere's low density means that even very fine particles settle faster than they would in Earth's denser air. But the settlement time is still long enough that the dust is effectively a persistent component of the environment. Second, particles this fine are strongly affected by electrostatic forces. Martian dust particles become electrostatically charged through triboelectric effects as they rub against each other and against surfaces in the low-pressure environment. Charged particles adhere to every surface they contact with a stickiness that is difficult to counteract. The Apollo program encountered this with lunar dust. Lunar dust was electrostatically charged, extremely fine, and had never been worn smooth by water or biology. It coated every surface it contacted, clung to suit fabrics and joint mechanisms, abraded seals through its angular microscopic structure, and proved nearly impossible to fully remove from suits and equipment. The crews reported that after EVAs, the lunar module smelled of gunpowder, the distinctive scent of freshly disturbed regolith. Martian dust shares the Apollo dust problem's key characteristics and adds additional ones. The perchlorate chemistry, the silicate particles with sharp microscopic structure, the reactive surface chemistry from iron oxides and perchlorites that have been exposed to ultraviolet radiation for billions of years. The suits will protect against direct skin contact and inhalation outside. But every EVA concludes with a contaminated suit entering the airlock. Airlock decontamination protocols reduce the dust transfer. They do not eliminate it. Over months and years, the accumulated transfer of trace amounts of Martian material into the habitat interior becomes significant. The air filtration captures the vast majority of airborne particles. The residual settles on surfaces, accumulates in crevices, adheres to equipment and fabrics. The crew will be chronically exposed to trace quantities of Martian material despite every precaution. And the thyroid implications of perchlorate exposure described above are not the only health concern. Chronic exposure to fine silicate particles, even at low levels, carries potential for lung tissue irritation and inflammatory response. The magnitude of the risk over multi-year exposure at low levels is not well characterized, because no human has ever experienced multi-year exposure to Martian dust at any level. The first crew will be the first. The cold on Mars is not merely uncomfortable. It is an engineering challenge that operates without pause for the entire duration of the mission. The average surface temperature at the Martian equator is around -80 degrees Fahrenheit or -62 degrees Celsius. Midday at the equator in summer can briefly rise above freezing at the surface. Nighttime at the same location drops to around -100 degrees Fahrenheit or -73 degrees Celsius. At higher latitudes and during polar seasons, temperatures fall well below -200 degrees Fahrenheit or -129 degrees Celsius. The habitat interior will be maintained at comfortable human temperatures. Life support systems heat the air continuously. The crew will not be cold inside the habitat. But the thermal management challenge is not about the crew's comfort. It is about the integrity of the boundary between the comfortable interior and the hostile exterior. Every component that creates that boundary undergoes a thermal cycle every sol. From the daytime operating temperature of the external components to the nighttime minimum and back. For a habitat at the equator, this cycle represents a swing of approximately 80 to 100 degrees Fahrenheit or 44 to 56 degrees Celsius per sol. Every seal, on every penetration through the habitat wall, goes through this cycle. Every cable that passes through the hull to connect external equipment to interior systems, every window frame, every airlock hinge and locking mechanism, every external equipment mount. All of it expands with the day and contracts with the night. Metal fatigues under cyclic thermal stress. Polymer seals harden and crack at the cold extreme and soften at the warm extreme. The mechanical properties of materials change with temperature, and cycling between temperature extremes degrades materials faster than static operation at any single temperature. Thermal cycling fatigue is the reason Antarctic research stations require constant maintenance and experience frequent equipment failures, despite being engineered for the environment. On Mars, the thermal cycling is more extreme than at any Antarctic station. The amplitude of the cycle is larger. The environmental chemistry is more reactive. Radiation, degradation of polymer materials proceeds in parallel with the thermal cycling, weakening seals and gaskets through a different mechanism simultaneously. The designers will have tested every component under representative thermal cycling conditions. The materials will have been selected for their documented thermal cycle resistance. The maintenance protocols will include regular inspection and replacement schedules for the highest wear components. Mars will still find the failure modes that the testing missed. Because laboratory thermal cycling, even extensive and rigorous testing, does not capture the exact combination of Mars-specific factors that the real environment presents simultaneously. The first crew will be the first people to find out where those failures occur. Water. Every mission depends on water in a way that makes the water system both the most critical and the most demanding to manage. The International Space Station imports all of its water. Every molecule consumed by every crew member over the station's operational lifetime was launched from Earth. The station recovers roughly 98% of water used in the habitat, primarily through the urine processing assembly and the water recovery system that captures moisture from the cabin atmosphere. The remaining roughly 2% that cannot be recovered is replaced by resupply. On Mars, resupply is not available. The percentage that is lost must be replaced by local extraction. Mars has water. The polar ice caps contain enormous quantities of water ice mixed with carbon dioxide ice. The polar layered deposits, which extend partway down from the poles, contain water ice in geological strata that have been building for millions of years. Orbital radar instruments on Mars Reconnaissance Orbiter and on ESA's Mars Express have mapped subsurface ice deposits at mid-latitudes, confirming that ice exists closer to the surface in many locations equatorward of the poles. The first crewed missions will be sited in locations where subsurface ice is accessible. The extraction system, part of the pre-deployed infrastructure that arrives on Mars before the crew, will heat the regolith to sublimate the ice and capture the water vapor, which is then condensed and purified. This process has been validated in laboratory conditions. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, on the Perseverance rover demonstrated that in situ resource utilization is operationally feasible in the Martian environment. But MOXIE was a proof-of-concept experiment, scaling water extraction to life support levels, maintaining extraction equipment in the field for years, and integrating it with the habitat's water systems is a different challenge from a laboratory demonstration. The subsurface ice at the mission site will not be exactly as the orbital surveys predicted. Subsurface ice is not a uniform layer. It exists in deposits that vary in depth, thickness, purity, and accessibility. The resolution of orbital radar remote sensing, while excellent for scientific purposes, is not fine enough to predict exactly what an extraction drill will encounter at a specific location. The actual ice, when the extraction system begins operating, will differ from the modeled expectation. The extraction rate will differ from the design rate. The crew will know, before they ever land, the projected extraction capacity. They will also know the uncertainty range around that projection, and they will manage water accordingly. Every liter extracted, every liter recycled, every liter used, every liter lost, tracked, balanced. Because the margin between sustainable and not sustainable is the measure of everything. Oxygen generation on Mars is linked to water in an intimate way. The primary pathway for generating oxygen in the habitat is electrolysis. An electrical current passes through water, splitting each water molecule into 2 hydrogen atoms and 1 oxygen atom. The oxygen goes into the habitat atmosphere. The hydrogen is typically vented or used in the Sabatier reaction to combine with carbon dioxide and produce methane and water, recovering some of the water that would otherwise be lost. This process requires water and it requires power. Both must be available continuously because the crew breathes continuously. The carbon dioxide scrubbing system works in parallel. Carbon dioxide is produced by the crew's metabolism and must be removed from the habitat atmosphere before it reaches concentrations that cause symptoms. At concentrations above roughly 1% of the atmosphere, carbon dioxide causes headaches, reduced cognitive performance, and disrupted sleep. At higher concentrations, it causes more severe symptoms. The scrubbing system uses amine-based or zeolite-based chemistry to capture carbon dioxide molecules from the airstream. The scrubber material is periodically regenerated by heating it, which releases the captured carbon dioxide and allows the material to be used again. The regenerated carbon dioxide can be vented or fed into the Sabatier system. The life support chain is long. Water extraction produces water. Electrolysis converts water to oxygen and hydrogen. Sabatier converts hydrogen and carbon dioxide to methane and water. The methane can be used as propellant or vented. The recovered water feeds back into the system. The scrubbers capture carbon dioxide. The power system drives all of it. Each step in this chain is a system. Each system has components that can fail, and the systems interact with each other in ways that can propagate a failure in one into problems across several others. Engineers call this tight coupling. When systems are tightly coupled, a perturbation in one propagates quickly through the whole network. Managing a tightly coupled life support system in a real environment where unexpected things happen requires continuous monitoring, rapid diagnosis, and effective improvisation. The crew will be trained for this. They will have managed failures in simulations, and the simulations will not have captured all of what Mars has to offer. Power is the master resource that everything else depends on. Lose power, and you lose life support. You lose water extraction. You lose food production in the greenhouse. You lose heating. You lose communications. You lose the ability to manage any of the other challenges. The power architecture of the first crewed Mars mission will have been designed through years of engineering, analysis, testing, and political negotiation. The primary design will likely combine large solar panel arrays with compact nuclear fission reactors. Mars receives about 43% of Earth's solar irradiance at the equator, less than half. This means that the panel area required for a given power output is roughly twice what would be needed on Earth. More panels mean more mass, more launch cost, more surface area to set up, and more area for dust to accumulate on. Dust accumulation on solar panels is the most persistent operational solar power challenge on Mars. The Spirit and Opportunity rovers both experience significant power reduction from accumulated dust throughout their missions. Opportunity saw power output reduced by up to 70% in heavy dust conditions compared to clean panel baseline. The mission survived through periodic natural cleaning events, gusts of wind that blew dust off the panels, and through careful power management. A crewed mission cannot depend on wind gusts for panel cleaning. The crew will have cleaning protocols, brushes, compressed gas systems, regular EVA, time allocated to panel maintenance. This maintenance adds to the operational load. It requires EVA time, which has its own costs and its own risks. And during a major dust storm, even perfectly clean panels produce very little, because the dust in the atmosphere between the sun and the surface absorbs and scatters solar radiation before it reaches the panels. The 2018 global dust storm, which lasted nearly 3 months and reduced solar irradiance at the surface to near zero at some locations, ended the Opportunity rover mission. Opportunity's batteries discharged. The rover never recovered. A crewed habitat in an equivalent situation, depending primarily on solar power, would be in a survival scenario. Nuclear power solves the dust storm problem. A compact fission reactor provides constant power output regardless of dust, time of day, or season. The Kilopower project has demonstrated a 10-kilowatt uranium-fueled fission reactor design, compact enough to be launched and landed on Mars. Multiple units in parallel provide the baseline power a small crewed habitat requires. The fuel lasts for years. The output is constant. The system is weather independent. But launching nuclear material from Earth requires extensive safety and regulatory processes. Enriched uranium, on a rocket that fails catastrophically during ascent, could scatter radioactive material over populated areas. This risk is taken seriously, as it should be. The review processes are extensive and add years to mission timelines. They are a non-negotiable part of the engineering reality. The power architecture of the first crewed mission will reflect whatever those processes produce, and it will be operated by a crew who understands its design thoroughly, in theory, and who will be learning its real operational characteristics on Mars. Because the real operational environment is not the laboratory where the system was designed and tested. It is Mars. And Mars has conditions that laboratory testing does not capture. Radiation on Mars is an area where the scientific data is unambiguous and the medical implications are significant. Earth is protected from space radiation by two overlapping systems working together. The global magnetic field, generated by convection currents in the liquid iron outer core, extends far into space and deflects the charged particle component of solar wind and the lower energy portion of galactic cosmic rays, preventing them from reaching the upper atmosphere. The atmosphere itself, roughly 33 feet of water, equivalent in shielding density, absorbs the radiation that the magnetic field does not deflect, including ultraviolet light, X-rays, and most of the remaining particle radiation. Together, these two systems reduce the dose at Earth's surface to roughly 3 millisieverts per year of effective dose from natural sources. Mars lost its global magnetic field billions of years ago. As the planet's interior cooled, the convective dynamics in the core that generated the dynamo shut down. Without a global magnetic field, the solar wind has been eroding the Martian atmosphere for billions of years. The result is an atmosphere that is 1% as dense as Earth's. The shielding it provides is equivalent to roughly 8 inches of water. Earth's atmosphere provides 50 times more shielding. The Curiosity rover's radiation assessment detector has been measuring the radiation environment on the Martian surface since 2012. The data it has produced is the most direct measurement of what the first crew will actually encounter. The average surface dose is roughly 180 to 225 micrograys per day. Adjusting for the biological effectiveness of the radiation types present on Mars, the effective dose on the Martian surface is approximately 230 to 250 millisieverts per year. The average effective dose from all natural sources at Earth's surface is about 3 millisieverts per year. The Mars surface dose is 30 to 60 times higher. Over a 500-day surface stay, the accumulated effective dose is substantial, adding the transit doses. From both the outbound and return journeys through interplanetary space, where there is no magnetic field protection and only thin spacecraft walls for shielding. The total mission, effective dose, significantly exceeds the career exposure limits that NASA currently applies to astronauts. Those limits are set to keep the excess lifetime cancer risk below 3% above baseline. The first Mars crew will exceed them. This is known in advance. It is a calculated risk. The alternatives are to not send people to Mars until better shielding technology exists, or to accept the elevated risk and go with what we have. Given that passive shielding, adequate for galactic cosmic rays, would require a mass of shielding material that is prohibitive, and that active magnetic shielding technology for spacecraft remains undemonstrated at the required scale, the practical path is to accept the risk. The crew will accept it with full knowledge of what it means. That does not make it a small thing. Galactic cosmic rays are the component of the radiation environment that poses the greatest long-term biological risk, and that is least amenable to shielding. These are not the relatively lower energy protons and helium nuclei of the solar wind. Galactic cosmic rays include heavy nuclei, the fully ionized atoms of heavy elements, including iron, silicon, oxygen, neon, and others, accelerated to velocities that are significant fractions of the speed of light by supernovae, active galactic nuclei, and other high-energy astrophysical processes. A single iron 56 nucleus traveling at 90% of the speed of light carries an amount of kinetic energy that is difficult to express in everyday terms. When it enters biological tissue, it does not interact with it the way X-rays do. X-rays travel through tissue, ionizing molecules along a track of random collisions. A high-energy heavy ion travels in a nearly straight line, creating a dense cylinder of ionization and physical damage along its path, like a bullet through living tissue at the atomic scale. DNA strands are broken along the entire track. Cellular structures are disrupted. The surrounding tissue responds with inflammatory signals, and unlike the scattered ionization from X-rays, which the body's DNA repair systems are fairly effective at addressing, the dense track damage from a heavy ion is much harder to repair correctly. Misrepair of complex DNA damage, where multiple breaks close together are repaired by joining the wrong ends, leads to chromosomal rearrangements that can drive carcinogenesis or cellular dysfunction. Studies at the Space Radiation Laboratory at Brookhaven National Laboratory have been exposing rodent subjects to simulated galactic cosmic rays using accelerated heavy ion beams for years. The results that have accumulated are not comfortable reading. Mice exposed to simulated galactic cosmic rays at doses comparable to a Mars mission show impaired performance on spatial navigation and memory tasks. They show increased anxiety, like behavior in standardized behavioral tests. They perform worse on tests of cognitive flexibility, the ability to adapt a learned behavior to changed conditions. They show elevated neuroinflammation, measurable increases in inflammatory markers in brain tissue. And critically, these effects appear at doses comparable to what a Mars crew would receive. Not at extreme doses, far beyond mission levels. At mission-level doses. The extrapolation from rodent neurology to human neurology is not direct. The mechanism of radiation damage at the cellular level is similar across mammals. The architecture of the nervous system differs substantially. Humans have larger brains with more redundancy. Human cognitive function may be more resilient to radiation-induced damage than rodent cognition at equivalent doses. Or it may not be. No human being has ever received galactic cosmic ray exposure at Mars mission equivalent doses. The data does not exist. The first Mars crew will generate it. Solar particle events operate on a completely different timescale from the background radiation and create a completely different risk profile. Background radiation accumulates slowly and continuously. The risk is chronic and cumulative. Solar particle events are episodic. They can deliver a large dose in a matter of hours. The Sun periodically releases large bursts of energetic protons during solar flares and the energetic particle components of coronal mass ejections. These events accelerate particles to energies of tens to hundreds of mega-electron volts and release them through the heliosphere. When a significant solar particle event is directed toward Mars, The proton flux at Mars increases by orders of magnitude above the background level within hours. The timing from the first observation of the event to the arrival of the peak proton flux at Mars is typically a few hours for the fastest particles, with the bulk of the fluence arriving over a period of hours to days. A very large solar particle event could deliver an effective dose of several hundred millisieverts to a crew member on the Martian surface within hours. At those levels, acute radiation syndrome becomes possible. Nausea, vomiting, fatigue, and changes in white blood cell counts in the days following exposure. At higher doses, more severe effects. The shelter protocol is well established. At the first warning of a significant incoming event, any crew member outside returns to the habitat immediately. Once inside, the crew moves to the storm shelter, a specially designed area of the habitat surrounded by additional shielding, typically water-filled panels and additional structural material, that reduces the dose rate during a solar particle event to a fraction of the open habitat rate. This protocol works. The shelter is effective. It requires the crew member to be able to reach the habitat and move to the shelter before the worst of the fluence arrives. A crew member who is far from the habitat at the time of an alarm or who is engaged in a task that cannot be safely abandoned mid-step, or whose suit has a problem that slows their return, has less margin. Space weather forecasting has improved substantially over the past 2 decades. Major solar particle events can often be predicted 24 to 48 hours in advance based on solar magnetic field observations and models. The prediction capability is real and valuable. It is not perfect. Events can exceed their predicted intensity. They can arrive faster than forecast. They can be directional in ways that models do not fully capture. The crew will know this. They will plan EVA operations with solar activity awareness as a standard factor. They will have abort-to-habitat protocols for EVAs during elevated solar activity. They will execute those protocols when required. And sometimes, the situation on the ground at the time of an alarm will not be the ideal situation that the protocol assumes. The medical situation deserves extended attention because it is where the gap between what the crew can do and what they might need is most concrete, and where the consequences of that gap are most immediate. The mission medical officer will be the most thoroughly medically trained person ever to go to Mars. Not a physician who took a few extra courses, a deeply capable medical professional who has spent years specifically preparing for the medical challenges of long-duration spaceflight. Flight surgeon-level training. Real surgical training, including operative practice, emergency medicine proficiency, pharmacology, for the conditions most likely to occur during the mission, radiology interpretation from portable imaging equipment, diagnostic laboratory operation, dental procedures, ophthalmology, psychiatric medication management. This training is real. The capability it produces is genuine. It is not equivalent to having a fully staffed academic medical center accessible 20 minutes away. The medical kit will be the most comprehensive ever assembled for a space mission. Medications for every anticipated condition, plus broad-spectrum coverage for unanticipated ones. Surgical instruments for abdominal, orthopedic, thoracic, and soft tissue procedures. Portable ultrasound for imaging. Blood analysis laboratory for hematology, chemistry, and infectious disease testing. Dental equipment, including extraction instruments and restorative materials. Ophthalmology tools for eye injury and disease management. psychiatric medications in appropriate quantities, emergency resuscitation equipment, blood typing and limited transfusion capability, wound care and burn treatment supplies, anesthesia capability, including regional and general options. The list is long. It represents years of consultation between operational medicine specialists, space medicine researchers, emergency physicians, surgeons, and the crews of previous long-duration missions. It will still not contain everything that a real medical situation on Mars might require. Because medicine does not divide cleanly into anticipated and unanticipated. Medical reality is continuous. A crew of 4, spending years in a radiation environment that elevates cancer risk, an immune environment that changes how infections present and how they are managed, a physical environment that creates new injury mechanisms, a low-gravity environment that changes how the body manages blood and fluid pressure, and a high-stress operational environment that affects sleep, appetite, and physiological resilience will encounter medical situations. Some will be straightforward. Some will be manageable with available resources. Some will require improvisation beyond what the training scenarios covered. And the improvisation will happen in a habitat on Mars, by a crew member with genuine but bounded training, with a communications link to Earth that adds 8 to 48 minutes to every exchange of information. Not the ideal conditions for a medical emergency, the only conditions available. Surgical situations deserve specific attention because surgery is a skill built through practice, and the practice available in pre-mission training is finite. Surgical competence is developed over years of operative experience. A surgical residency in a specialty like general surgery typically lasts 5 years, during which a resident participates in hundreds of procedures of varying complexity under the guidance of experienced surgeons. A trauma surgery fellowship adds additional years of experience managing the most complex and time-sensitive surgical situations. The Mars Mission Medical Officer will have received intensive pre-mission surgical training. They will have practiced procedures on high-fidelity surgical simulators. They will have operated under guidance in real surgical environments to the maximum extent that the mission preparation timeline allows. They will be substantially more capable than a layperson. They will not be equivalent to a trained surgeon with years of operative experience. The gap matters in a scenario where a crew member requires emergency abdominal surgery on Mars. Appendicitis, a perforated bowel from a traumatic injury, an intestinal obstruction, a ruptured ectopic pregnancy. These are scenarios that a general surgeon manages routinely in an equipped hospital with an anesthesiologist, a scrub nurse, a circulating nurse, post-operative intensive care, and blood bank backup. On Mars, the surgical team is the medical officer and whatever assistance the other 3 crew members can provide while also managing the habitat systems. The operating environment is the medical bay of a pressurized habitat. The anesthesia is what was brought. The blood backup is the limited transfusion capability in the kit. The post-operative intensive care is whatever the medical officer can provide while also continuing to manage the mission. The training will have prepared the medical officer for this. The preparation is not equivalent to the resources of an Earth hospital. This is not a failure of mission planning. It is the unavoidable consequence of being on another planet. The crew will manage it. The outcomes will be what the available resources and the medical officer's capability produce. And some outcomes will be different from what they would have been if the patient had been on Earth. Food matters in ways that go well beyond nutrition. Every human being has a relationship with food that is embedded in culture, in memory, in social ritual, in the sensory experiences of flavor, texture, and smell, and in the basic daily experience of something pleasant in a day that may otherwise be difficult. The mission will carry a food supply, engineered for shelf stability, nutritional completeness, and caloric adequacy. The packaging will maintain food quality for years. The nutritional content will have been carefully designed to provide the full range of macro and micronutrients the crew needs. It will be real food, not paste in tubes. It will be the best that food science and space nutrition expertise can produce for a long-duration mission. After months of eating the same rotation of packaged meals, prepared the same limited ways, in the same small habitat, the crew will think about food differently than they expected to before the mission. This is not speculation. It is documented consistently across every long-duration mission in the history of space exploration. Crew members who return from long missions consistently identify food as one of the most significant factors in quality of life and morale. Not nutrition. The experience of eating. The pleasure of variety. The sensory satisfaction of flavors that surprise you. The comfort of food that connects to cultural memory. On the International Space Station, which has regular resupply missions that occasionally include fresh food items, crew members describe receiving fresh vegetables or fruit as a significant event, something that improves the mood of the entire crew. The first crewed Mars mission will have a greenhouse. This is recognized as a mission-critical element, not just a nice addition. Fast-cycling crops, lettuce varieties, spinach, radishes, green onions, herbs like basil and cilantro and mint can be grown in hydroponic systems and harvested in weeks. The greenhouse will be small relative to the crew's food needs. It will supplement, not replace, the packaged food supply. But what it provides goes beyond its contribution to the daily calorie count. The smell of fresh basil in a habitat surrounded by rust-colored desert. The visual presence of green, living plants. The act of tending to a garden, even a small one. Harvesting something you grew. Eating something fresh. These experiences matter. They are documented to matter in isolation research on Earth. On Mars, they will matter even more. And when the greenhouse system develops a problem, when a component fails or a crop is lost, the loss is felt beyond its nutritional dimension. The experience of permanent sensory confinement is something that is difficult to convey to someone who has not experienced a long-duration isolated deployment. 4 people. A habitat. A planet that cannot be stepped outside of without a suit. No new environments, no new faces, no random encounters, no weather that can be enjoyed rather than just managed, no animal sounds, no human crowds, no change of scenery beyond the immediate horizon visible through the habitat windows. The same walls, the same sounds, the same smells, the same people, every soul, for years. Isolation research has been studying this for decades. Antarctic winter-over crews stay at remote research stations through the polar winter, which can last several months. They are isolated from the outside world in ways that share some characteristics with a Mars mission, though the duration is shorter and rescue is more accessible. The psychological patterns that emerge in Antarctic winter-over populations are well documented. An initial phase of high motivation and cohesion. a midwinter decline in mood, activity, and interpersonal quality, increased irritability, sleep disruption, a phenomenon called winter over syndrome, a cluster of mood and behavioral changes that appear to be driven by the combination of social isolation, light deprivation, and confinement. Naval submarine deployments provide another data point. Submarine crews operate in an extremely confined space for deployments that can last months. They have limited communication with the outside world. They are underwater, in an environment that is also immediately lethal without the submarine's protection. The psychological literature on submarine crews documents the patterns of adaptation that develop over a deployment, the coping strategies that work, and the failure modes when they do not. Mars 500, the most relevant simulation study, confined 6 subjects in a mock spacecraft and Mars habitat for 520 days. The subjects knew the simulation could be ended at any time. They were on Earth. No actual spaceflight. No actual Mars. Despite these conditions, which are far less stressful than an actual Mars mission in most respects, the crew showed significant changes in sleep, activity, and psychological measures over the course of the study. Some subjects showed near-normal adaptation. Others showed significant deterioration in sleep quality and activity levels that persisted for most of the study. The data from Mars 500 is genuinely valuable for mission planning. It also illustrates the limits of simulation. None of the subjects in Mars 500 were managing an actual life-threatening environment. None of them were actually on another planet. None of them had given up the option of ever returning to Earth. The actual Mars crew will have all of these differences from the simulation, and the psychological consequences of those differences cannot be fully modeled from simulation data. The social dynamics of a 4-person crew confined in a small habitat for years on another planet is a challenge that receives substantial attention in mission planning, and that is still not fully solvable. The crew will be selected with extraordinary care for compatibility. They will train together for years before launch, building real familiarity, genuine working relationships, mutual knowledge of each other's professional styles, communication patterns, and stress responses. They will enter the mission with realistic expectations. They will have conflict resolution protocols established in advance. They will have a communication channel to a mission psychologist on Earth. They will have had more preparation for the social challenges of the mission than any crew in the history of spaceflight. And friction will still develop. Because friction is a property of close confinement over time, not a failure of preparation. Irritations accumulate. Habits that were neutral in the early mission become aggravating by month 18. Differences in communication style that were easily managed in the training environment become persistent, low-grade friction when there is no break from them. Small resentments that would dissipate easily in a normal social environment, where you can choose not to interact with someone for a day, do not dissipate when you cannot choose that. The crew will manage these dynamics. They will manage them because the mission requires it. Because they depend on each other for survival, and that dependency is a powerful incentive to maintain functional relationships. Because they are professionals who chose this mission knowing what it would involve. But the management has a cost. Sustained management of interpersonal tension, the constant effort of maintaining professionalism when you are frustrated, of being constructive when you would rather not be, of prioritizing the team's function over your own emotional preferences, is exhausting. It is a form of cognitive and emotional labor that does not stop. Over years, it accumulates. And the accumulation affects everything else. Sleep quality, cognitive performance, decision quality, patience for operational demands, resilience when things go wrong. The social environment and the operational environment are not separate. They influence each other continuously. A crew with excellent social dynamics manages operational challenges better. A crew under sustained social stress manages them worse. Mission planners know this. They design for it. And Mars will test the designs. The communication delay is both a practical operational constraint and a daily psychological experience that the crew will live with for the entire mission. At Mars's minimum orbital separation from Earth, the one-way signal delay is roughly 3 to 4 minutes. At maximum separation, it is roughly 20 to 24 minutes. When Mars is near conjunction with the Sun, signal degradation makes reliable communication impossible for weeks at a time. For routine mission support, the delay means that every question sent to Earth and every answer received takes a round-trip time of 8 to 48 minutes minimum. This is workable for non-urgent situations. For emergencies that require expert input, the delay is significant. A medical emergency that requires guidance from a specialist on Earth is managed with guidance that arrives 8 to 48 minutes after the question was sent. By the time the guidance arrives, the situation has evolved. The crew must act on the situation as it was when they sent the question, updated by their own ongoing assessment, incorporating the response when it arrives. This is manageable, but it is not ideal. For the crew's personal relationships, the delay creates a communication experience that is qualitatively different from what most people have experienced. Real-time conversation does not exist. You record a message and send it. You receive a response message hours later. The exchange takes place in segments separated by signal lag. A conversation that might take 10 minutes in real time takes hours of elapsed time, with each participant recording their part separately and waiting for the other's response. This is asynchronous communication. It was how humans communicated by letter for most of history. It is emotionally different from real-time communication in ways that people who have relied on real-time communication for their adult lives will find significant. The crew will adapt. Humans are adaptive. But the adaptation has a cost in the quality of the relationships they are maintaining across the distance. The crew will find things on Mars. This is the part of the mission that the operational challenges exist to enable. Mars holds a geological and potentially biological record stretching back to the earliest period of solar system history. The planet's surface preserves environments that no longer exist. Ancient river valleys, now dry and windswept, carved by liquid water that flowed billions of years ago. Lake basins where water pooled and sediment accumulated for long enough to leave clear geological signatures. Hydrothermal systems where heat from Mars's early volcanic interior drove chemistry that, on Earth, would be associated with microbial life. Every rover mission has deepened the picture of ancient Mars as a place that was, at minimum, not inhospitable to life. Whether Mars ever had life is the question that a human geologist, standing in those ancient environments, with human eyes and human judgment and human hands picking up rocks, is best positioned to begin answering. Not robots, not remote sensing. Humans. A geologist in the field makes observations that a rover cannot make. They see patterns in rock outcrops that require perspective and context to interpret. They recognize significance in textures and structures and compositional variations that require the pattern recognition of a trained eye. They make the judgment calls about what is worth examining more closely, what is worth sampling, what changes the expected narrative of the geology. Curiosity and perseverance have done extraordinary science on Mars. They have done it slowly, with limited reach, and without the interpretive capability of a trained human scientist standing at the outcrop. The first crew member who looks at a Martian outcrop and says, "Wait, this does not fit the expected stratigraphy here," and whose follow-up investigation produces a finding that reshapes what we understand about ancient Mars, will have done something that changes the trajectory of science. And they will have done it while also managing the full operational reality of living on Mars. The science and the survival are not separate tracks. They share the same crew, the same time, the same attention. A crew managing a habitat systems problem has less capacity for science. A crew that is well and functioning efficiently has more. The operational challenges are not obstacles to the mission's scientific purpose. They are the conditions under which the mission's scientific purpose must be pursued. The day the crew steps outside for the first time, the first genuine EVA on the Martian surface, is a moment that the training scenarios have approached but cannot replicate. You have practiced this in simulations, hundreds of times. Suit-up procedures, airlock cycling, EVA navigation, sample collection protocols, equipment operation, emergency abort procedures. All of it rehearsed until the steps are automatic. And still, the moment the outer airlock door opens and you step out onto the surface of Mars for the first time, the experience will be different from the simulation. Not in the procedures. The procedures will work exactly as trained. In the totality of it. The sensory reality of another planet. The vast landscape that the rover cameras gave you a ground-level perspective of, but that standing height transforms into something different. The curved horizon. The pale butterscotch sky. Your shadow on red-orange dust. The suit pressure against your body. Your own breathing, loud in the helmet. The checklist waiting. And the knowledge that you are the first human beings to stand on this ground. Experienced pilots, test pilots, astronauts who have done EVAs, all describe the experience of genuine high-stakes operations as qualitatively different from the most realistic simulation. Not because the skills do not transfer. They do. But because the full weight of the real situation, the actual stakes, the actual environment, the actual irreversibility of what you are in, produces a cognitive and physiological state that simulation does not replicate. Adrenaline in a simulation is not the same as adrenaline in the real situation. Both are real. They are not the same. The first Mars EVA crew will be operating in that real situation, with everything they know, everything they have trained for, and in conditions that no training produced. The physical demands of EVA operations on Mars add another layer to the already substantial physical challenge of being there. Mars suits are pressurized systems. A pressurized suit is stiff. The internal pressure of the suit pushes against every joint, every connection, every point of movement. To bend your arm at the elbow in a pressurized suit, you work against the pressure of the suit, trying to maintain its pressurized shape. To grip a tool, you work against the pressure in the glove, that wants to return the hand to its neutral, relaxed position. To walk, every step requires more deliberate effort than walking in shirt sleeves. Training in simulated pressure suits, in neutral buoyancy tanks that simulate the low-force environment of weightlessness, and in Earth analog terrain, provides the procedural knowledge. The experience of those suit mechanics in Mars gravity, on actual Martian terrain, is different from any simulation. Mars gravity is 38% of Earth's. This means your effective weight is substantially reduced. Your mass, your inertia, is the same. But the downward force is less than half of what you are accustomed to. Walking in reduced gravity, with a pressurized suit on irregular terrain, where rocks shift underfoot and slopes behave differently than their appearance suggests, requires ongoing balance and coordination management. A stumble in a Mars suit is a serious event. A fall could damage the suit. A fall in difficult terrain could injure the crew member. Either outcome triggers an emergency response and terminates the EVA. The terrain around the habitat will have been imaged extensively from orbit and from surface level before the crew arrives. The crew will know the terrain. They will not know every rock underfoot until they step on it. Every EVA involves managing a physical environment in a constrained, pressurized suit under reduced gravity, on terrain that is never quite what the imagery predicted. This is not a dramatic danger. It is a persistent operational management challenge. Every EVA. For years. The return journey will come. After the surface stay, after the return window opens, after the ascent vehicle lifts from Mars, the crew faces another 7 months in transit. And when they finally reach Earth, they will land in bodies that have accumulated the full cost of the mission. The radiation exposure is documented. Its full consequences will not be known for years, because some radiation-induced health effects take years to manifest. The bone density losses will require months of intensive physical therapy to partially recover. Some loss may be permanent. The cardiovascular reconditioning will take similar time. The vision changes, if they have occurred, may be permanent. The full scope of neurological effects from galactic cosmic ray exposure will not be fully characterized for years, possibly decades, as the crew is followed medically through the rest of their lives. And the psychological return to Earth will be its own distinct challenge. People returning from extended isolated deployments, including long-duration space missions, consistently describe the re-entry to normal social environments as difficult in ways they did not anticipate. The sensory intensity of Earth after months in a quiet, controlled habitat, crowds that feel overwhelming, sounds that feel too loud, the density and complexity of normal human social life that feels like overload after the stripped-down social world of the mission. The world continued while they were gone. New things happened. Old things changed. The accumulated context of daily life that they missed is not something that a briefing can fully restore. They rejoin a conversation that has been going on without them. And they carry everything the mission gave them. Not just knowledge, not just data, the experience of being on another planet, of living where no human had lived, of facing what no training could have fully prepared them for, and of doing it anyway. What the first Mars crew will face is not a list of solvable problems. It is a continuous encounter with a planet that does not adapt to human needs. The training is real, and the preparation is serious, and the engineering is the best humanity can produce. And still, Mars will be more than any of it fully anticipated. Not because the engineers and scientists and mission planners did not do their jobs well. They will have. But because a real environment is always more than the models that describe it. Because the combination of challenges, all of them present simultaneously, all of them interacting with each other, all of them demanding from the same finite pool of human resilience and attention and physical capacity, produces an experience that cannot be simulated. Only live. The radiation and the dust and the cold and the pressure management and the medical uncertainty and the communication delay and the social confinement and the food and monotony and the wrong light and the wrong sky and the knowledge that Earth is a point of light in the dark above them. All of it. Every soul. And through all of it, the science, the geological fieldwork, the sample collection, the atmospheric measurements, the search for what Mars might tell us about where life can exist in the universe. All of it pursued in the real conditions of another planet, not in a simulation, not from orbit, but on the ground, by humans who are there. This is what they will face. This is what no training program can fully prepare anyone for. And this is what makes the first Mars crew something genuinely singular in human history. Not just the first humans on another planet. The first humans to know, from direct experience, what it is actually like to be there. That knowledge does not exist yet. They will be the ones who create it. And when they come home, what they bring back will be more than samples and data. It will be the lived knowledge of what Mars actually demands, what it takes, what it gives, what it costs, and what it is like to face all of that, in a suit, on rust-colored ground, under an alien sky, with Earth sitting in the dark above you as a bright blue star. That is what they will face, for all of us. The habitat will not feel the same in month 1 as it does in month 12. This is one of the things that the training scenarios approach but cannot replicate, because even the longest pre-mission isolated deployment analogs are measured in months, not years. The first month on Mars will feel, by all accounts from isolation research and from the experience of astronauts on long-duration ISS missions, energizing. There is so much that is new. The novelty of the environment, even through the habitat windows, even in the limited views available from the airlock and during EVAs, provides stimulation. The operational routine has not yet settled into genuine routine. Everything still requires conscious attention because nothing has been done before. The science is generating immediate results that are exciting. The crew is functioning well. The systems are performing to specification. The sense of historic significance is present and motivating. This is the phase that mission planners see in simulations. The early mission, high-functioning period. It is real. It does not last indefinitely. By month 6, the novelty has worn away in ways that accumulate gradually but add up significantly. The terrain through the habitat windows is familiar. The operational routines are genuinely routine. The same systems are checked the same ways on the same schedule. The same food is prepared in the same limited ways. The same 4 people are at the same table for every meal. The same sounds fill the habitat every day. The systems that are working well have been working well for months, and their continued good performance has become background rather than foreground. The things that are not working perfectly, the persistent minor systems issues that every complex machinery generates, The small medical concerns, the interpersonal friction, these are now foreground. This is the pattern that every isolation study documents in populations that stay long enough to see it. The early mission performance is not the representative performance. The representative performance is what happens when the novelty is gone and the routine is established and the long duration stretches ahead with no visible endpoint. That is where the mission really begins. And that is where the gap between training and reality is largest. The concept of operational tempo is something that is easy to underestimate from the outside. Mars missions will be planned at high operational density. The science return per unit of mission time is maximized. The crew's schedule will be full. Not oppressively full, because maintaining crew well-being is itself a mission priority. But full. The EVA schedule, the sample analysis schedule, the habitat systems maintenance schedule, the communications schedule, the exercise schedule, the food preparation time, the scientific documentation, the operational planning and replanning as conditions evolve. All of this fills the soul. And the soul is 24 hours and 39 minutes. The crew needs roughly 8 hours of sleep. They need time to eat. They need personal time that is genuinely personal, not scheduled activity of any kind. The remaining time is the working day. And the working day on Mars contains more simultaneous requirements than the pre-mission schedule estimated. Because the pre-mission schedule was built around idealized operational conditions. Real conditions generate surprises. A piece of equipment that requires unplanned maintenance. A weather development that changes the EVA plan. A medical situation that requires attention. A systems anomaly that needs investigation. Each of these arrives on top of the planned schedule. The crew adapts. Priorities are renegotiated. Some planned activities are deferred. Others are accelerated. The constant re-optimization of the schedule against a reality that does not follow the plan is a form of cognitive labor that is present every single soul. And it is tiring. Not dramatically. Persistently. The kind of fatigue that does not feel like anything specific, but that accumulates underneath everything. That makes the minor irritations slightly more irritating. That makes the difficult decisions slightly harder to make. That makes the recovery from operational stress slightly slower. Managing this fatigue is one of the things that mission planning explicitly addresses. Mandatory rest periods. Crew-controlled personal time. Reduced scheduling density to provide margin for the unplanned. And still, in the real mission, the margin will sometimes be insufficient. Because the real mission is not the planned mission. It is the planned mission as modified by Mars. The suit operations deserve extended attention because the suits are the interface between the crew and the Martian environment. And every EVA is a sustained engagement with a system that must perform perfectly for hours at a time. A Mars EVA suit is not like the suits used on the International Space Station. EVA suits, while complex and capable, are designed primarily for microgravity operations. They are not designed for walking on a planet. Mars surface suits must handle a different set of demands. They must allow bipedal locomotion on irregular terrain. They must provide enough mobility in the legs and hips for extended walking. They must maintain their structural integrity through falls and abrasions that are likely on rough Martian terrain. They must manage the thermal environment in a cycle from Martian day to Martian night. They must handle the electrostatic properties of Martian dust without the dust working its way into suit joints and mechanisms. And they must do all of this while maintaining the pressure differential that keeps the crew member alive. The engineering of Mars surface suits is one of the most challenging technical problems in human spaceflight. The requirements are contradictory. Flexibility requires thinner, lighter materials. Pressure containment requires strong, heavy materials. Thermal regulation requires insulation that adds mass. Dust resistance requires sealing mechanisms that reduce mobility. Every design choice is a trade-off. The suits that the first crew uses will represent the best available resolution of these trade-offs as of their development date. They will be remarkable engineering achievements. They will also have limitations. Limitations in dexterity. A gloved hand in a pressurized suit glove can grip and manipulate objects, but with substantially reduced sensitivity and fine motor control compared to a bare hand. Tasks that require delicate manipulation, like working with small fasteners, connecting electrical connectors, or handling fragile samples, will be harder and slower in a suit glove than in shirt sleeves. Limitations in reach. A pressurized suit constrains the range of motion of every joint. Some orientations that are possible for the bare human body are not possible in a suit. This affects the range of positions the crew can achieve during EVA tasks. And limitations in duration. EVA suits carry finite consumables. Oxygen. Power for the suit, electronics. Water for the cooling system. The duration of an EVA is bounded by these consumables. Extended EVAs require extensions or returns to the habitat for resupply. Managing consumables against the tasks to be accomplished is a constant EVA planning challenge. The crew will become skilled at this management over the course of the mission. In the first EVAs, the management is less fluent. Experience builds fluency. But the first EVAs, the ones where the mission's most significant early discoveries are most likely to occur, are also the ones where EVA operational fluency is at its lowest. This is unavoidable. It is the condition of being first. The geological context of the landing site will be more complex in reality than in the orbital survey. This is a consistent finding from every robotic Mars mission. The orbital imagery provides a good large-scale picture. The ground-level reality adds detail and complexity that the orbital scale cannot resolve. The landing site will have been chosen through extensive analysis. Orbital spectroscopy, radar mapping, high-resolution imaging, and trajectory analysis will have identified a site that is scientifically interesting, accessible from a landing trajectory perspective, near accessible water ice, and relatively safe for landing. All of these factors will have been evaluated as carefully as the orbital data allows. The ground-level reality will be different in detail. Rocks that appear smooth from orbit will have their own surface textures and compositions. Geological contacts that appear as lines in orbital imagery will be transitions that have width and complexity when examined up close. The stratigraphy visible in cliff faces and crater walls, which orbital imagery reveals in broad outline, will have a detailed structure visible to the crew at ground level that the orbital data did not capture. The crew will be discovering the geological reality of their landing site over the course of the mission. Every EVA adds to the ground-level picture. Every sample analyzed adds chemical and mineralogical detail. The scientific picture builds progressively, and sometimes what builds is surprising. A geological contact that is more complex than expected. A mineral composition that does not fit the predicted stratigraphy. A structure in the rock that does not have an obvious explanation in the known Mars geological framework. These surprises are scientifically valuable. They are also operationally demanding. An unexpected finding requires investigation. Investigation requires additional EVA time, additional sample collection, additional analytical laboratory time. The mission schedule is revised. Priorities are renegotiated. The science leads, and the operations follow. This is how it should work. And it adds to the operational complexity that the crew manages every soul. The atmosphere of Mars is not just an oxygen-free environment that kills you without a suit. It is an active participant in the operational environment. The Martian atmosphere carries dust. It creates wind. It generates weather. Not weather in the Earth sense, with fronts and precipitation and dramatic temperature changes driven by moisture. But weather in the sense of atmospheric state, changes that affect operations. Dust devil activity is common on Mars. Dust devils form when solar heating of the surface creates strong convective updrafts that entrain dust from the surface and spin up into rotating columns. They can be small and brief. They can also be substantial, reaching thousands of feet in height and spanning hundreds of feet across, carrying enough dust to noticeably reduce visibility and deposit significant amounts of material on solar panels and exposed surfaces. Dust devils passing over the habitat and EVA areas are a routine operational reality. They can interrupt EVA operations when visibility drops. They can deposit enough dust on solar panels to require cleaning before scheduled operations can proceed. They can carry abrasive dust particles into suit joints and mechanisms if a crew member is caught in a significant one. The regional weather patterns on Mars, the seasonal variations in atmospheric dust loading, the daily cycle of convective activity, will be partially predictable from orbital observations and surface meteorological measurements at the habitat site. They will not be perfectly predictable. A dust devil that forms and moves in an unexpected direction, or that is larger than typical for the season, or that occurs at a time when the crew is outside and not positioned to deal with it immediately, adds to the operational surprise load. Mars generates surprises, not dramatically, persistently. The water recycling system will run continuously for the entire mission. Every drop of water recovered from human metabolism, from the cabin atmosphere, from condensation, from biological and cooking processes, will be captured, processed, and returned to the potable water supply. The International Space Station's water recovery system achieves roughly 98% recovery efficiency under nominal conditions. The water lost to the system is replaced by resupply. On Mars, resupply is not available, and the recovery efficiency is not constant. It varies with the operational state of the system, with the maintenance status of filters and membranes, with the quality of the water being processed, with the load on the system from the crew's activity level and hydration needs. Managing the water budget means tracking every input and every loss continuously. If recovery efficiency drops below the design specification, the loss rate exceeds what extraction can replace, and the reserve begins to draw down. Identifying why efficiency dropped, diagnosing the system component responsible, and restoring performance is a maintenance task that requires understanding of the system's chemistry and mechanics. The crew will have received detailed training on the water recovery system. They will know how to perform maintenance on every component. They will have the tools and the spare parts required for planned maintenance tasks. And they will encounter failure modes that the training did not cover, because the training covered the anticipated failure modes. A real system, in a real environment, generates unanticipated failure modes. The response is diagnosis, improvisation, and repair. In a system as critical as water recovery, the pressure to restore performance quickly is high. And the tools available are what was brought from Earth. Nothing more. The medical officer will function as the crew's only healthcare provider for the duration of the mission. This is a role that carries a specific kind of weight that is worth understanding clearly. The medical officer is responsible for the health of the other 3 crew members and for their own health simultaneously. Medical self-assessment, the ability to evaluate one's own symptoms and functioning accurately, is genuinely difficult. People are not good at assessing their own health objectively. They underreport symptoms that might indicate serious problems. They attribute fatigue to obvious causes rather than investigating whether it might have a medical component. They delay seeking treatment for conditions that would send them to a clinic immediately if they were on Earth. These tendencies are even more pronounced in people who are motivated by a desire not to disrupt the mission. The medical officer who develops symptoms, whether from radiation effects, from infection, from the cumulative physiological stress of the mission, or from an underlying condition that was not identified in pre-mission screening, faces a particular challenge. They must evaluate themselves. They must make the judgment call about whether their symptoms warrant investigation and treatment. They must do this while also managing the healthcare needs of the other 3 crew members. And they must do it in an environment where drawing attention to their own medical concerns has implications for the mission. Not because the other crew members would respond negatively, because the medical officer knows how important their own function is to the rest of the crew. The mission psychologist on Earth will provide support through the communication channel. Earth-based physician advisors will be available through the same channel. But the real-time assessment and the real-time decision-making belongs to the crew. And sometimes the person who most needs medical attention is the person who is most reluctant to acknowledge it. Mission planning addresses this through crew health monitoring protocols that provide objective data. Daily physiological measurements, regular cognitive assessments, biomarker tracking through blood and other samples analyzed in the Habitat laboratory. The objective data supplements the self-report. It does not replace clinical judgment in the presence of an actual symptom picture. And clinical judgment in this environment belongs to a crew member who is also a patient. There is a specific psychological phenomenon associated with long-duration, isolated deployments that does not have a widely known name, but that mission planners and isolation researchers are very familiar with. It is sometimes called the psychological closing phase. As the anticipated end of a mission approaches, the crew's attention shifts toward the return, toward Earth, toward the people they are going to see, toward the things they are going to do when they get back. This shift has a paradoxical effect on performance and cohesion. At the moment when the crew should be approaching maximum proficiency, having spent months or years developing operational expertise, their attention is partially elsewhere. The mission is not over. The operations continue. The science continues. The maintenance continues. The risks are the same, and the crew is, in a measurable sense, already on their way home in their heads. This phenomenon is observed in Antarctic winter overcruise, in submarine deployments, in long-duration ISS missions. The behavioral and performance effects are real. They are not dramatic. They are statistically measurable across populations of long-duration mission participants. Mission planners are aware of this. They design the end of mission period with explicit attention to maintaining operational engagement and focus. The science schedule is maintained. The safety protocols are maintained at the same standard as throughout the mission. The crew is encouraged to stay focused on the mission rather than on the return. But the psychological closing phase is not fully addressable by scheduling. It is a feature of human psychology in situations of extended isolation. The first Mars crew will experience it. They will manage it. And it will add one more layer to the operational complexity of the final period of the mission, at the precise moment when the complexity of departure preparations is already adding to the load. The departure from Mars will be one of the most dangerous moments of the mission, perhaps the most dangerous. The ascent vehicle, pre-positioned on the Martian surface by the pre-deployment sequence, will have been sitting on Mars for years by the time the crew reaches it. Years of thermal cycling, years of radiation exposure, years of dust accumulation, years of Martian chemistry acting on its materials. The vehicle will have been designed to survive all of this. The pre-deployment systems will have been monitoring it throughout. Pre-launch checks will confirm its readiness, and it will have never been tested in its actual operational configuration, with a crew aboard launching from the actual Martian surface. The launch will be a first flight, not a first design. The design will have been extensively tested. But the combination of this specific vehicle, in this specific launch configuration, at this specific site, after these specific years of Mars exposure, launching from Mars for the first time, is a first flight. And first flights carry uncertainty that subsequent flights do not. The ascent will be fast. The vehicle will accelerate from 0 to orbital velocity over the course of a burn measured in minutes. The crew will experience the forces of ascent after years in partial gravity. Their bodies will not be at peak physical condition for tolerating acceleration loads. The bone density losses, the cardiovascular deconditioning, the muscular changes. All of these affect how the body handles the stresses of rocket ascent. The launch profile will have been designed to minimize peak loads. The crew will have been doing specific physical preparation in the weeks before launch. But the preparation is working with bodies that have spent years on Mars, not bodies at the condition they were in when they trained for ascent on Earth. The departure from Mars is the moment when everything the mission asked of the crew's bodies comes to a point. And the outcome depends on engineering and biology that have never been combined in exactly this way before. What they bring back, not the samples, not the data. What they themselves carry back in their experience, in their changed understanding of what it means to be human in the universe, is something that has never existed before. No human being has ever lived on another planet and returned. No human being has ever had the experience of looking back at Earth from the surface of another world. No human being has ever accumulated the specific combination of physiological adaptations, psychological experiences, and scientific knowledge that a Mars surface stay produces. The returning crew will be the first, and what they carry will not be fully expressible. Not because they cannot articulate it, because the experience has no referent in the experience of anyone who has not been there. Astronauts returning from long-duration ISS missions describe a shift in perspective that is real, but that they consistently find difficult to communicate to people who have not experienced. Spaceflight. The overview effect. The perspective shift that comes from seeing Earth as a sphere from space, from understanding viscerally, rather than just intellectually, that Earth is a whole object floating in nothing, is described consistently across decades of astronaut reports. It is real. It changes people. And even people who have experienced it describe having difficulty conveying it to those who have not. The Mars crew will have had an experience that is categorically beyond what any ISS astronaut has experienced. Not just in duration, not just in distance, in the fundamental quality of what it means to have been somewhere, to have stood on another planet, to have worked and struggled and lived on ground that no human foot had ever touched, to have seen Earth as a point of light from the surface of another world, to have faced every soul the full weight of what it actually takes to be human in a place that was not made for humans, and to have come through it. What the first Mars crew will face is not really reducible to a list of challenges. It is the totality of an experience that no human being has had before, an experience that the training can approach from many angles, that the preparation can address in many dimensions, that the engineering can support in many ways, and that Mars itself will exceed in ways that none of that fully predicted. This is not a failure. It is the condition of being first, of going somewhere that no one has been, of creating the knowledge through living. That is the only thing that makes the next crew better prepared than the first. The first crew will face it. Not because they were born to it, not because they are exceptional humans in some mystical sense, but because they were selected and prepared for it as carefully as human institutions can select and prepare, and because they chose it with full knowledge of what they were choosing. That choice, that willingness to face what cannot be fully anticipated, is what has driven every significant human exploration. Every ocean crossing before the maps were complete. Every mountain ascent before the summit was known. Every mission into the dark. Mars is the next dark. And the first crew will carry human experience into it, with training that could not fully prepare them, with equipment that could not fully protect them, and with the human capacity which has never needed full preparation or complete protection to go somewhere worth going. They will face it, and it will be enough. The suits themselves represent one of the most intimate technical relationships any human being will ever have with a piece of engineering. You trust them with your life, not abstractly, concretely. Every time you walk out of that airlock, the suit is the only thing between your biology and an environment that would end you in seconds. That relationship between the crew member and their suit develops over the course of a mission in ways that the pre-mission training gives a foundation for, but that the mission itself completes. The crew will know their suits the way a pilot knows their aircraft. They will know every idiosyncrasy, every quirk of the environmental control system, every point in the suit mechanisms where resistance is slightly higher than nominal, every part of the helmet that fogs slightly under certain humidity conditions, every detail of how the suit behaves in the full range of conditions they take it into. This knowledge is earned by doing it, by actually wearing the suit in the actual environment, by experiencing how it performs when the temperature drops during the late afternoon EVA, by learning how the dust accumulates on the visor at different dust loading levels. By finding out how the gloves behave when they are cold versus when they are warmed by EVA work. None of this is in the training manual. It accumulates through experience. And it accumulates in an environment where a gap in that knowledge, an unknown behavior of the suit, in a situation not yet encountered, can matter immediately. The habitat systems will be the most intimately known technology the crew has ever operated. Not because they are the most complex, but because the crew will interact with them every single day for the duration of the mission. Every pressure reading, every temperature reading, every atmospheric composition measurement, every flow rate in the water recycling system, every power output and load reading, every oxygen generation rate, every carbon dioxide scrubbing efficiency measurement. The crew will develop an intuitive sense of what their habitat systems feel like when they are running correctly. A change in the sound of the air circulation system. A slight shift in the readings from the life support monitors. A subtle change in the smell of the habitat air. These cues will become meaningful over time in ways that the pre-mission training could not fully instill. Because the training environment is not the actual habitat operating in the actual Martian environment. The actual habitat running in the actual Martian environment has its own specific signature, its own specific normal operating pattern that the crew will learn by living with it. This deep familiarity with the systems is one of the most valuable things the mission accumulates over time. An experienced crew, 6 months into the mission, is more capable of detecting and diagnosing a subtle systems anomaly than the same crew was on landing day, because they know what normal sounds like. And they know, intuitively, when something is different. That knowledge is the product of 6 months of daily intimate operation. It cannot be installed in a training program. It has to be earned on Mars. The question of what happens if a crew member decides they cannot continue, not because of a medical emergency, but because of a psychological limit that has been reached, is one that mission planning addresses carefully and that does not have a clean answer. The selection process will have screened for psychological resilience. The preparation will have addressed the psychological demands of the mission as thoroughly as any program has ever addressed them. And still, human beings have limits. The limits are not always knowable in advance. They depend on the specific combination of stressors, on how those stressors interact with the individual's specific psychological architecture, on what the particular mission throws at the crew in its specific sequence. An individual might handle all of the challenges separately. The combination, in sequence, over time, might exceed what that person can sustain at full function. This is not a failure of the individual. It is the nature of human psychological limits in extreme environments. If a crew member reaches a point where they can no longer function at the level the mission requires, the options are limited. The rest of the crew, who are already operating at their own capacity limit, must absorb some of the load. Mission controllers on Earth can provide support and can revise operational demands. Medical interventions, including psychiatric medications, can address some manifestations of psychological decompensation. But evacuation is not an option. There is no mechanism for removing one crew member from Mars and returning them to Earth before the mission window opens. The crew member stays. The crew manages. The mission continues. This is one of the hardest aspects of Mars mission planning to engage with directly, because it involves acknowledging that the crew may face psychological situations for which the only options are imperfect. This does not mean the situation will occur. The selection process is real, and the preparation is serious. Most crew members will function effectively for the duration. But planning honestly for human spaceflight means planning for the full range of human outcomes. And the full range includes this. The way time feels on Mars is something that no isolation study can fully simulate, and that no crew member's account from a previous mission can fully transmit. It will not feel like a month has passed. Not the way a month feels on Earth, with its variety of experiences and changing contexts and social texture. It will feel like a large, undifferentiated block of time has accumulated, and the calendar will say it has been a month. The markers that normally give time its felt quality on Earth, the weekends that are different from weekdays, the seasonal changes, the social calendar of events and gatherings, the variety of environments as you move through your week, the random encounters that give each day a different texture from others. None of these exist in anything like their Earth form. The souls accumulate. The work continues. The systems are checked. The EVAs are conducted. The samples are analyzed. The meals are eaten. And at some point, the crew notices that several months have passed in what felt, from inside, like a much shorter period, or much longer. The subjective experience of time in isolated, confined environments is known to be unreliable. People consistently misjudge elapsed time. They may feel that weeks have passed when it has been months, or that months have passed when it has only been weeks. The loss of reliable time perception is documented in isolation research. It has practical consequences for the crew. Planning and motivation depend on a sense of where in the mission you are. If the subjective experience of time diverges significantly from actual elapsed time, the crew's planning and their emotional relationship to the mission timeline can be affected. Mission planning builds in explicit time anchors. Weekly milestones, monthly reviews, milestone events tied to specific soul numbers. These help. They are working against a psychological reality that does not fully yield to scheduling. The physical reality of what it feels like to put on a suit and step outside of a pressurized habitat into a near vacuum every day for months is something that takes on a different quality over time. In the early mission, each EVA carries the charge of what it is, going outside on Mars. The first time. The second time. The first time you reach a geological formation that looked significant from the habitat window. The first sample collection. The first instrument deployment. Everything is still new. The suit-up procedure is deliberate and careful, because you are still learning it. The airlock is a threshold that you approach with awareness of what you are crossing. By month 6, the EVA is still serious. It is still something you prepare for carefully. But it is also routine in the way that any frequently repeated professional activity becomes routine. The suit-up is done from procedural memory. The airlock is crossed with the same awareness, but without the charge of novelty. You step outside into the alien environment with proficiency. And the psychological challenge of that routinization is subtle but real. The routine is appropriate. It represents genuine expertise. But expertise can carry its own risk, the risk of becoming too comfortable with something that remains genuinely dangerous. Experienced pilots describe this. The moment when you are experienced enough to know exactly what you are doing, and therefore capable of slightly less vigilance than the beginner who does not yet know. The suit is still the thing between your biology and the environment that kills you. The checklist is still the thing that verifies the suit is working. The airlock cycling is still the procedure that maintains the pressure boundary. None of that changes. The relationship the crew develops with these procedures, the managed familiarity that maintains rigor without excessive vigilance, is one of the most important things they will learn to calibrate on Mars. And calibrating it in a real environment, with real stakes, is something that training can only approach. The science that the first crew returns will change human understanding of our solar system in ways that are genuinely difficult to predict in advance. This is the nature of first-hand investigation in previously unvisited environments. You find things you were looking for. You also find things you were not looking for. The unexpected finds are often the most significant. Curiosity found complex organic chemistry in the Martian regolith. Not expected. Enormously significant. Perseverance found evidence of past aqueous environments in the Jezero crater delta that was more detailed and more definitive than orbital data had suggested. The human geologists of the first crew will stand in environments that rovers have not reached. They will make the field observations that only a trained scientist on the ground can make. They will collect samples that the sample analysis return mission will eventually bring to Earth, laboratories where the full analytic power of terrestrial science can be brought to bear on Martian material. Some of those samples will answer questions humanity has been asking about Mars for decades. And some will raise questions that nobody thought to ask. That is what happens when humans go somewhere with their full cognitive and physical capability. They discover things that change the map. And the fact that the crew is discovering those things in the conditions described throughout this account, under the radiation, under the operational pressure, under the social confinement, under the physiological stress, with all of that as the context for their work, is not despite those conditions. It is through them. The discovery is the mission. The conditions are what the mission costs. And the crew will pay that cost, soul by soul, and do the work that is the point of paying it. This is what the first Mars crew will face. Not a sequence of problems. Not a list of challenges to be ticked off and solved. A sustained, continuous encounter with a planet that does not care about human needs. That does not adjust to human limitations. That presents its conditions without modification, every soul, for the duration of the mission. Training prepares people to encounter known challenges in practiced ways. Mars is full of challenges that no training fully anticipated. The combination of everything described here, the radiation and the dust and the thermal cycling and the water management and the power dependence and the medical isolation and the communication delay and the social confinement and the food monotony and the circadian disruption and the wrong light and the wrong sound and the constant low-level vigilance about suit and habitat integrity, all of it simultaneously, day after day, in a place where Earth is a point of light. That is what they will face. And they will face it because they chose to. Because the selection process identified people capable of choosing it clearly and pursuing it fully. Because the preparation built the skills and the mental frameworks that make the encounter survivable and productive. And because something in the human character, the same something that drove people across oceans before the destinations were known, across continents before the maps were complete, into the deep ocean and to the poles and to the moon, drives people to go where no one has been and find out what is there. The first Mars crew will find out. For all of us. And what no training can prepare them for, they will handle anyway. because that is what the first always does. Good night.